Let's have a look at problem 773, sliding puzzle. This is a daily challenge problem, and it's also marked hard by LeetCode. Actually, if you practice more for this kind of problem, so you can use Breadth First Search to solve it. So here, our purpose is to demonstrate how to solve this problem in a better way. So basically, how to encode the configurations of the border state and how to get the number of steps to get the target, right? So here the move consists of choosing 0 and a 4 directional adjacent numbers and adjacent number and swapping with it. So here the final state is this one, 1, 2, 3, 4, 5, 0. So this is regarded as solved. So we want to return the least number of moves required so that the state of the board is solved. So because it involves the least number of moves, or in graph language, you can see the shortest path from the current state to the final state. So therefore, we can think of Breadth First Traversal. So here are several examples. So the first example, you can switch 0 and the number 5, you get the final state. So the number of steps to make it solved is 1. And in the second example, so you cannot solve it. So this is -1. And in the third example, you can output 5. So this is the detailed explanation. So here, the constraints, the first 3 actually is about the board, right? So we have a 2x3 board, and there are 5 numbers. There are 0, and each value is unique. So with that said, we are ready to talk about the strategy. First, the overall strategy. So let me make some annotations here. The overall strategy will be Breadth First Search because it involves shortest path, right? So here, actually, it's corresponding to the least number of moves. As such, we need to have a way to monitor the state of the board, right? So because here we have only 6 numbers, actually we can use a string to represent it. For example, in example 1, the original state can be represented as 1, 2, 3, 4, 0, 5, right? So the target state, the target we are going to get is this one. So it's 1, 2, 3, 4, 5, 0, right? And then each time we can locate the position of empty or 0, and then we can switch with its neighbors. So because here also we have a very small board, we can actually for each index, for example, here this is 0 index, 1, index 2, and index 3, 4, 5. If we use the string, 1D string as the representation of the board state, then we can know the positions we are going to swap. So let's write it like this. So the board can be represented index 0, index 1, index 2. So this is the first row in the 1D string representation. So the second row will be 3, 4, 5, right? So then you can see if you are currently here, this is the 0 and 0 state, you can swap with the neighbors 1 and 3. So 1 and 3 corresponding to the index in the 1D3 representation, right? So then we can make a dictionary, right? So if you are in the 1D string representation, if the 0 is at index 0, so you can switch with the index 1 and index 3. So here let's write index 1, index 3. So if it's at index 1, so here it can be switched with 0, 2, and 4, right? 0, 2, and 4. Let's write down this dictionary, right? Because we don't want to make a dynamical swapping in the process of Breadth First Traversal. So similarly, index 2, so it can switch with 1 and 4, right? 1 and 5, right? So let me write here 1 and 5. So similarly, 3, the index 3 can be swapped with 0 and 4. So here by swap we mean the corresponding numbers in the 1D string, right? And for 4, so we can swap with 1, 3, and 5. So 1, 3, 5. And for the index 5, we can swap with 2 and 4. Right. So this is our main treatment. So first we are going to use a 1D string to represent the body state, and then the swaps available for a number if the number of 0 corresponding to index C1, then you can swap with the numbers in the 1D string with index 0, 2, or 4. So this way we are going to produce a new state, and then we can use standard BFS. So next, so it's BFS. So as long as we consider BFS, typically the queue data structure is going to come into play, right? Abstract data is going to come into play. So these are the main ideas. First, the big idea is breadth first traversal or breadth first search, and then there are two parts. First, we are going to use a 1D string to represent each state of the board, and then also we make a dictionary so that we can track how we can do the move or swaps. So with that said, we are ready to do the coding. So actually the coding will be very straightforward. So let's write a standard breadth first traversal solution. First, we're going to get the target. So the target will be this one, right? So the target. Let me copy this part. So the current state is given by the board, right? So you can join using this string. So basically, string number for row in board for number in row. So this corresponds to to 1, 2, 3, 4, 0, 5. Let me print out 1 so that you can get a feeling about the state. So this is for example 1. You have 1, 2, 3, 4, or 5, right? So now we can set up the first we can get these neighbors, right? This is how we are going to do the move or swap. So this is one part. Another part is that we are going to have a queue. So we're going to use a deck object to monitor to mimic the queue behavior. So the queue is going to store the state and the number of moves to get the state. So originally, because we use state, so it's 0. Okay, we are going to store state, the body state, and number of moves, so least number of moves to get that state. So originally, for sure, this is a natural number 0, right? Then also, in order to avoid repetitions, so we're going to use a set to monitor this process. Then with that set, we are ready to do the standard while loop. So if the queue is not empty, so we're going to get the state, the moves, number of moves is going to be queue pop left. So we are going to use the left as a head of the queue and the end as a tail. So each time if we want to enqueue something, we are going to append, right? Then we are going to pop from the left. So this is our current state. Then first thing is to check if state equals the target. If so, we are going to return the moves, right? This is the stop condition check. And otherwise, so we're going to check if the state not in visited. Actually, this is redundant, but let me write it like this so that we can make sure. So we we avoid repetition. So if state is not invisited, so we're going to add the state to the visit. Then from this state, we're going to consider its neighbors through one move. So first, we're going to get the zero index, right? So the zero index will be state, the index, this is the string number, right? And then we are going to consider neighbors correspond to this index. So basically for neighbor in neighbors, so zero index. So then we can consider do a move. So let's construct the new state. First, the new state, we can make a list out of the original state. And then for this neighbor index and the zero index, let me write like this. Neighbor index, the zero index, we can swap. So basically the new state. So because now it's a list which is mutable, so we can do this swap. So the zero index and the new state, the neighbor index, and we can swap these two. So in Python we can do like this. So once we swap these two states, we get a new state of the board. So what we are going to do is to build a new state string. So it's going to be the John, right, of the new state. So once we get this, what we are going to do is to check if we have already visited this state or not. If not, we are going to enqueue it. So let's see, let me use a new state string to distinguish, right? If new state string not invisited, that's because here we are check that. So here we can choose not to use this if statement, or you can also consider to add the state to the visitor set at the very beginning, but there's some small details. So if this is not visited, so what we're going to do is we're going to do append the new state string, and then we need to increment the moves by 1. Then once this done, so if during the while loop we have got a final state or the target, means that the sliding puzzle is solved. So we should have already returned something. Otherwise, we're going to return -1. So this is the full solution to this problem. Let's do a quick check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So here, let's give a quick summary of this problem. So first, the main thing or the main hint for the strategy is here. Return the least number of moves. So when you think of this least number of moves as the shortest path to the solvable state, then this leads you to think about Breadth First Traversal. The second thing is that we need a better way to represent the border state. So this here we are using a 1D string, and then we use this neighbors map or dictionary to know how to do the move or do the swap. Once this is done, basically the code is the standard Breadth First search or Breadth First traversal code. With that said, I guess that's about it for the current video. You're welcome to follow up our other videos for practicing the lead code problem. Thank you.